Hello everyone. Today we will see how extra sum of squares principle works. We have already seen it in application. We have seen that there also we use f-test. So today we will try to theoretically prove it. So what we do in the extra sum of squares principle is that we try to break down the regressors that we have into two parts. For example, if my matrix of regressor values looks like this, so x11, x21, x31, xn1. Similarly, I have x12, 22, n2, and so on. Finally, I have x1k, x2k, xnk. This is my x matrix, right? We know that this corresponds to x1 as a regressor, this corresponds to x2 regressor, this corresponds to xk, and this is my interceptor. Okay. So what we are trying to do now is, suppose we have certain regressors which we feel are perhaps not useful in the model, they are redundant, they are not adding much value to the existing model, then we want to test for it. So we break down our regressor matrix into two parts, x1 and x2, correct? Now, how do I do that? So basically we rearrange the columns of X matrix in such a way, because we know that in the general regression model, order of the regressor doesn't matter. So we rearrange the columns of the X matrix in such a way that the variables whose redundance we want to test are part of this X2, which is like a second part of my X matrix, and variables which I want in the model, which I feel are useful, are in the x1 part of this X matrix. Okay. Now, how do we proceed? So we are going to use the same result that we have been using so far. That is, the distribution of the quadratic form follows chi-square, etc. But for that, we need to define what is this extra sum of squares. So we have defined regression sum of squares in the past. So our full model consists of entire X matrix. So regression sum of squares corresponding to this full model will be beta hat prime x prime y, correct? Because this beta hat prime is 1 cross p, this is p, sorry, this is, yes, p cross n, and this is n cross 1, so finally I get 1 cross 1. So beta hat prime x prime y minus n y bar square, correct? That is my regression sum of squares for full model. Now we consider the reduced model, the one where the redundant variables are dropped. So for this reduced model, my regressor matrix is simply x1. So this regression sum of squares corresponding to this reduced model will be beta hat prime based on this reduced model. So let me call it beta hat prime red. Then this x1 prime, y remains the same, and since y remains the same, y bar also remains the same. Okay. What is beta hat for the reduced model? Let me write. So beta hat for the reduced model will be x prime x whole inverse x prime y, but in terms of reduced model. So it will be x1 prime x1 whole inverse x1 prime y. This is my beta hat reduced, correct? So if I now want to consider difference between these two regression sum of squares, now first question, which regression sum of squares is going to be large, the full model or the reduced model? So we know that we have more regressors in the full model. So of course, even if it is not significant, still there is going to be a larger contribution. So I would write the extra sum of squares as sum of squares due to regression for full model minus sum of squares due to regression for reduced model. Okay. The term n y bar square is common in both, so it will get cancelled. So we'll be left with beta hat prime minus beta hat reduced prime into, no, I cannot take even x prime common. Okay, so let me write. So this becomes beta hat prime x prime y minus beta hat reduced prime x1 prime y. Okay, I have x1 here. So let me substitute values of beta hat. Okay, so I'm left with beta hat is x prime x whole inverse x prime y. So prime of that will be y prime x, then x prime x whole inverse is symmetric, so it stays as it is. So I have this x prime y as it is. Beta hat prime reduced will be y prime x1, then x1 prime x1 whole inverse, and then x1 prime y. Okay. What I can do now is I can take y prime outside. So I'm left with x prime x whole inverse x prime minus x1 prime x1 whole inverse x1 prime, and then this y. Okay. So I seem to be in a setup where I have y prime some matrix into y. And the result that we saw in the earlier lectures is, if I know my y is normally distributed with mean 0 variance v, where in this case I know variance is sigma square I, and we know that if A into V is an idempotent matrix, then I get something. Okay, then I have y prime ay as something. So let me check if this matrix is idempotent. So I have x prime x whole inverse x prime minus x1 prime x1 whole inverse x1 prime. Okay. First of all, is this a symmetric matrix? Now we know that this matrix, if I take its transpose, it is x prime x whole inverse x prime, which is exactly the same matrix. So this is symmetric, this is symmetric. As a result, difference is also symmetric. For idempotent, I will need to check the product. So x prime x whole inverse x prime minus x1 prime x1 whole inverse x1 prime. Okay, so what do I get? So if I take the product, I will have x prime x whole inverse x prime. Then from this I will have x prime x whole inverse x prime. This is first term. Then minus x prime x whole inverse x prime, and then from this second term I get x1 prime x1 whole inverse x1 prime. Then the next term is from this term as well as this term, so I will get x1 prime x1 whole inverse x1 prime into x prime x whole inverse x prime, and then plus x1 x1 prime x1 whole inverse x1 prime into x1 prime x1 whole inverse x1 prime. So I have x prime x whole inverse and x prime x here, so this gets cancelled. Similarly, x1 prime x1 and x1 prime x1 whole inverse, this gets cancelled. Okay. Okay. Now, if I look at this term, then we know the result for partition matrices which we saw in the first online lecture, that is x prime x inverse x prime into x1 if I have. So this is basically just x1. Okay, we have seen this result. Check the first lecture on sum of squares in regression. Similarly, this x1 prime x prime x whole inverse into x prime, this is simply x1 prime. Okay, so this also comes from the same result, the product of the partition matrices. So what do I get? What I get is, let me write, this is equal to, from the first term I will have x prime x whole inverse x prime. From the second term I will have x1 prime x1 whole inverse x1 prime. Then I have minus x1 prime x1 whole inverse x1 prime plus x1 prime x1 whole inverse x1 prime. So this term gets cancelled with this term and I'm left with the matrix with which I started. So we have just now proved that this is an idempotent matrix. Now this is an idempotent matrix, but what my V is sigma square into I, right? What I want is AV should be idempotent matrix, correct? So I will need my A to be actually this matrix in the bracket divided by sigma square, because then only A into V will be idempotent. Okay, so the result that I have will now be that y prime into this y divided by sigma square, that is my extra sum of squares divided by sigma squares will have chi-square distribution with some degrees of freedom, okay, and lambda. So what are the degrees of freedom? The degrees of freedom are same as the rank of this matrix. So for getting degrees of freedom, I'll need to consider rank of the matrix in the bracket. So because this is an idempotent matrix, rank will be same as the trace. So let me write trace of x prime x whole inverse x prime minus x1 prime x1 whole inverse x1 prime. Okay. So what is this? This I could write as trace of first matrix minus trace of second matrix. So trace of x prime x whole inverse x prime minus trace x1 prime x1 whole inverse x1 prime. Okay, we will use the properties of trace. So this is same as trace of bicyclic reshuffling x prime x inverse x prime x minus trace of x1 prime x1 whole inverse x1 prime x1, correct? So I have trace of, now this is an identity matrix, okay? this is an identity matrix of order P, because X is of order P. Here order matters. Okay. Trace of IP minus trace of, this is also an identity matrix but of order whatever is the remaining order. So for example, my in my x1, that is the remaining number of regressors that I have in my model, is suppose R. Okay, then this becomes trace of I R. Okay, so this is P minus R. So what I have is extra sum of squares follows extra sum of squares divided by sigma square follows chi-square with P minus R degrees of freedom, and then we can pair it up with error sum of squares from the full model, and we can test the ratio to have F distribution. Okay, so let me stop here for today. Thank you.